to save those daily folders and post?
No, you guys have to remind me to upload it. But if you remind me, I can upload those folders.
I will remind you.
Most of the time I get an email like during the class, someone's gonna send me the notes, using a smartphone. So by the time we get into the office, it's like, okay, all right, I have to upload the notes now, the files. I wish there's a way, for me to easily work with a file that is already on the server, but it's not, well, I haven't set it up yet. There's a way to do it, but I haven't set it up yet. Okay, let's get back to here. Make sure, but that's why I saved the files, just in case, I do not record it, at least the files will still be captured. This is question number 3. And then we start a new window. We do have 2 variables, x and k. Now in this case, there's a specific initial condition. So let me go back to, let's get rid of this, it's not being used. There we go. Get that one ready. Yep, this is the one. Okay, there's a specific, precondition. X is 3, y is 21, and k is -5. 3, 21, -5. I forgot one column here. Y. And I can't remember the terms. 3, 21, -5. 3, 21, -5. That's really the precondition, not line 1. All right. Now we can start to trace. Algorithm, trace. All right, we're ready to go. Line 1 has to evaluate the condition, x is less than y. Is that true or false? X is 3, y is 21. That is true. So that means which line do we have to go next? We have to go to line 2. Line 2 is asking x is less than y. Is that true or false? True again. Go to line 3. Line 3 says x gets x minus k. So what is 3 minus -5? We get 8. Then we go back to line 2. X is less than y is true again because 8 is less than 21. We have to go back to line 3 again. This is just, it's the same as adding 5, right? So it becomes 13. Go back to line 2. X is less than y is still true. Go to line 3. So you have to do this a few times. X is 18. And then one more time, we get 23. Go back to line 2. X is less than y is false. Now what do? We get out of the loop. And the loop is the only thing in the then branch of the conditional statement. What do we do after we finish one branch of a conditional statement? We go to whatever line is after the conditional statement, but since there's none, we go to post. So that's why we end the execution of the program right there. There are a few common mistakes that people make. One common mistake is we have to go back to line 1. No, we don't go back to line 1 because line 1, 5, and 9 indicate the outermost construct is a conditional statement. As a conditional statement, you don't go back. It is a one-shot deal. Is that okay? The second mistake that most people make is forgetting about this line here. This row in the trace is important. You cannot go from line 3 of row 11 to post, okay? Because line 3 is inside a loop, and you cannot just say, okay, I'm done, but you're still in a loop. There's no way to end a program's execution when you're still inside a loop. You have to go back to line 2 because line 2 is the only part where you can say, okay, should I go through another iteration or should I get out of the loop? Okay, this time we get out of the loop. And that's why this line 2 or the tracing of line 2 of row 12 in the trace is important. Okay, that is significant. Yep, question?
So the only way you would go to line 5 down would be if it came out false.
If I go to line 5, okay, if I make x greater than 21 to begin with, or greater than or equal to, then I will go to line 6. I don't trace line 5 here because I don't trace line 5 or line 6. So in that case, I'll go straight to line 7. Let's do that. Okay, I'll use sheet 3, just to show that particular scenario. Okay, so I will just go ahead and change x to be something a little bit bigger. Okay, let's say 28.
Now, what I was just asking was, once you got to the one step completed, you just skip the rest of it, just go to post, correct?
Sorry?
So once you got to where you were, you wouldn't have to worry about the rest of it, you just go straight to post.
Well, let's go through this trace and find out. Okay. All right, so we still have to go to line 1. X is less than y is false this time because 28 is less than 21 is false. So that means we don't go to line 2. Instead, we go to quote unquote line 6. But we don't trace line 6, okay? Because line 6 is just a marker of the beginning of a post checking loop. By itself, it doesn't do anything. So we don't trace line 6. We trace line 7 instead. Line 7 says x gets x plus k. X is 28. K is -5. 28 plus -5 is 23. After line 7, we go to line 8. Line 8 is significant because it has a condition to evaluate. X is less than y is false because 23 is less than 21 is false. Then where do we go? Go back to line 7 because this is a post checking loop. You check the condition, then you decide whether you want to go back for another iteration or not. Line 7 is going to add 23 and -5. The sum is 18. Then we go back to line 8. X, which is 28, is less than y, which is 21, is finally true. But because this is a post checking loop, the condition is called an exit condition, which means when the condition is true, we get out of the loop. So what do we do next? Go to post. Is that okay? So in the same example, I'm illustrating 2 scenarios. One going for the then branch starting on line 2, and the other one goes to the else branch, which quote unquote starts at line 6, but you don't trace line 6, we trace line 7 instead. Yep.
Depending on the program, you have different forms of post and pre-check loops, correct?
Sorry?
And depending on the language you're using, you have different pre-checks and post-check loops, like
That is correct.
do while versus
Repeat until.
the until.
Yeah, repeat until comes from Pascal. Pascal only has repeat until as a post checking loop, but in C it is do while, and in do while the condition is a stay in loop condition. So that means when the condition is false, then you get out of the loop. But in this class, I just use repeat until because I think repeat until is more colloquial. It's more commonly used in on a daily basis. We basically say, okay, you don't want to do something else until you're done with this. Okay, but we don't use do while as often as a in natural language. Yep.
What does C++ have for?
C++ uses do while, so you do have to invert the condition because the condition specifies when do you stay in the loop as opposed to when do you get out of the loop. But otherwise, it's the same construct. You still check the condition after you perform the body of the loop. So you still have to perform the body of the loop at least once, just like with a repeat until.
You say whether it's checking for true or false?
In do while, which is the way C does post checking loops, if the condition is true, you stay in the loop, so you go back to the beginning.
C++ does what?
Do while.
So it's true, you check for true. Or it's going to be, it's true, it returns. Comes back.
Okay, that is still kind of confusing because it's in C, C++, and most C-derived languages, When the condition is true, you stay in the loop. When the condition is false, you get out of the loop.
They're both the same.
Yes. C, C++ are the same. They are the same for the most part. C++ can be seen more or less as an extension on C. So whatever is true in C is typically true in C++, except for certain little things. Right, so this program is done. And we are moving on to the last one, which is question number 4. We'll pick this one. Okay, question number 4 is really fun. So fun that sometimes I don't get the answer right away. All right. So this is, the question asks you to give me examples, okay, of, what kind of value of x and y can result in z being 0? What kind of combination of x and y will give me z equals 1 at the end of the algorithm, z equals 2, z equals 3, and so on, okay? So this means, you have to think of test cases where lines 2, 4, 6, 8, 10, or 12 will execute. So for each case, you have to give me a concrete example of x and y. Does everybody understand the nature of the question? If a branch is not possible, you just have to kind of briefly explain why it is not possible. All right, so let's go ahead and work this one out. I'll just use a text editor for this. This is path. Okay. There you go. All right, so this is for question number 4. So I'll say 4. Oops, 4 first. All right, so let's go ahead and get started. Okay, let's do the case where z equals to 0, which means line 2 has to execute. So what do you think will make line 2 execute?
Y equals 6.
X equals 3 has to be true, and y equals 6 has to be true as well, right?
That's just 2 times.
That's 2 times, yeah. The asterisk means multiplication. Yep. Is that okay so far? Okay. How about making z equals 1, which means, how can I make line 4 execute out of this multi-branch conditional statement?
X equals 3.
X equals 3. Now you
Y
cannot
is
just
not
say x equals 3, because if you just
Y
say
is not
x,
6.
and y has to be non-6. Yep, not 6. So y has to be different from 6, but since I'm asking for concrete examples, that works. Okay. All right, z equals 2. Okay. How can I make line 6 execute?
X equals 4. Y equals 6.
Well, y has to equal to 2 times x.
Oh.
X equals
4.
4, and y equals 8, right? Because y still has to be twice the value of x. They can both be 0, okay? If you make x equals to 0 and y equals to 0, that works here too. Okay, so there are tons of examples that will make that work. All right. Z equals 3. Now this one is a little bit tricky because instead of an and, we have a or over here. So the question is, can we still make this happen? The answer is no, we cannot make that happen. Why?
Because it's only hot. It is 2 branches.
Okay. Yep.
Because you've already delegated paths from 3 and 5 to catch the OR case.
Right. So this is impossible because x equals 3 is already caught, right? By you can refer to a line number. So x equals 3, all cases are already caught by line 1 and 3 together. then the case of y equals 2 times x is also caught, all cases are caught by lines 1 and 5. If you look at lines 1 and 5, line 1 will cover the case where it's very specific, and line 5 will catch all the other cases. So that means it is impossible to make that condition true at this point. Are we doing okay so far with the explanation? So you have to make the explanation specific enough to basically say, oh, okay, so I can see now why it is not possible, because between these lines and these lines, it would have covered all the cases that will make this particular condition true. All right, so if z equals 3 is not possible, doesn't that mean everything after that is also impossible? And we can just say, okay, we are all done here. No. We can make one particular branch impossible, but future branches can still be possible. So let's take a look at what will make z equals 4. Okay. Z equals 4 requires that x is less than 3. Okay. Can I make x is less than 3 true, but still make all of the other conditions false? Absolutely, right? X could be 0. And y cannot be 0, but y can be anything else. Why can't y be 0?
Because we've already caught that condition in the previous range of y being double of x.
Yep, because x equals 0 and y equals 0 is already caught by line 5. Line 5 will catch that case, because when x equals 0 and y equals 0, y equals 2 times x, and it will be caught by line 5. So z would end up with a value of 2 instead of 4. But y can be anything else. Y, as long as y is not twice of x, in this case, it will still be okay. So y can be 1. Okay, what about z equals 5? Can we make all of the previous conditions false, except so that I can go all the way to the else on line 12? Yeah, there are tons of cases like that. I just have to make x greater than 3 and make sure that y is not twice of that. Right? So x equals 4 and y equals 4 should do it. But you have to double check. The nice thing about your concrete examples is you can double check, right? If x equals 4 and y equals 4, the condition of the first line will fail because x does not equal to 3. The second condition on line 3 will fail. The condition of line 5 will fail. The condition of line 7 will fail because it is neither of these is true. The condition of line 9 will fail. So that means we have no choice but to go to the else, and z will end up with a value of 5. Is that okay? So that's the answer of question number 4. And you kind of have to remember this is question 4C. So let me just double check and save the file again as question 4C. And then the other ones are also specific to a particular version of the question. So you kind of have to make sure that you match the answer to a particular question. Are there any questions about the exam? Now you will have more questions, but each question, some of the questions will be shorter, because instead of giving me the entire trace, you only have to trace a few steps. So I will give you, the partial trace up to a certain point, and then you will have to finish up the trace. So you will encounter more questions, but I think it's a good thing because from your perspective, it means if you make a silly mistake with one, it's not gonna impact the test overall, too much, because it's just one question out of 8 or something like that. I have not decided on the number of questions yet, but that's to be determined. Any questions about tracing? About the practice test? And this is not really a practice test. This was the test from last semester. Yep.
Can we do something similar to question number 2?
yes, there will be something similar to question number 2, but question number 2 does require the entire thing, because it's kind of hard to, just work on one particular link of the whole thing. So I'll probably make it not as mundane, not as, not a whole lot of chore, but more, reasoning in it. Okay. Are there any other questions? No other questions? Well, we still have Tuesday to ask questions because the exam is on Thursday. It will be here, in the classroom. It will be paper-based. I will give you space on the exam paper itself to write your answer. But if you think that you might want additional pieces of paper, bring it. You will need a writing instrument. I prefer pen, because it doesn't smear, it's not erasable and stuff like that. You might want to bring a ruler just in case, in your own trace, you can line it and you'll have your own columns. You won't need a calculator because, we'll just be adding and subtracting simple numbers. It's open book, open notes, anything that is either handwritten or printed prior to the test, you can bring it in. You can bring in a textbook if you want. It's individual, okay? So everyone is supposed to work on his or her own test. I cannot think of anything else. I mean, it's going to last the entire duration of the class. If you finish early, you can leave early. Okay. Any other questions you want to ask about the test? No? Okay. So if there are no questions about the test, we are going to move forward and start on a new topic in Moodle. I don't know what happened to my browser. Did I close it? Must have. Okay, let's go to.
Since you went recording when you did number 2, could you do another one on number 2 so you can have recording?
Redo it? I'll look into it. How are you guys going to take other classes when things are not recorded? One student told me that not only is the lecture not recorded by the professor, but the professor refused to let anyone do any recording in the class. So there are classes like that where you cannot bring in a recorder and just put it on a podium and say, okay, I just want to record the audio portion of the class, and that's still better than nothing. The professor can deny that and say, no, I don't want you to do any recording in my class. The question is, can a professor do that or not? Yes?
Yes.
I don't know. I do not know.
It's in the bylaws. It's in the bylaws.
It's in what?
It's in the bylaws.
Bylaws of the college?
The professor can refuse to be recorded, but you have to ask them before you record them.
Interesting.
If you don't, you're actually subject to litigation.
Wow.
Yeah.
Well, you guys are not subject to litigation by watching the YouTube.
Reminds me of the movie Real Genius.
Why?
The fact is that it comes in, the student comes in one time, he's saying there's a whole bunch of students. The next time he comes in, the professor is lecturing and all the students are recording. There's all thing is in this classroom and those students are just recording devices. The third time he comes in, recording devices, and the professor is also playing a recording. The professor's not there. He's the only one in the class.
I could have done that. I could have taught this class out of recordings from past semesters, right? But that wouldn't be fun. Okay, so we are moving on to this new topic called top-down design. Top-down design is one of those things where, well, you guys should know it already because we do this type of thing all day long, doing different things. It's just, why does it apply to programming and how do we apply that to programming? So the first thing we'll do is to explain, the rationale of top-down design. Why do we have this kind of concept of top-down, instead of bottom-up? Or, why do we need structure altogether? Okay, so that's the first thing I want to explain. To kind of give you an analogy of without top-down design or without hierarchy of one thing containing other things, it's kind of like giving you a 3 terabyte hard drive, which I think you can buy for how much now? Huh? 170.
Yeah.
Okay, so for $170 you can buy a 3 terabyte hard drive. But if I give you a file system that does not have folders, and in other words, you have to put every single file into the root folder, like C:\\, how useful would that 3 terabyte hard drive be?
Terrible.
Well, unless you have one single file that is 3 terabytes, then it will still be okay, right? But if you don't have one single file that is super huge, because even if you store all the ISO files of movies, DVDs and stuff like that, let's just say you're doing that legally, you own every single DVD that you're making a copy of. Okay, for DVD, each DVD is only about 8 gigabytes. Okay, so you divide 3 terabyte by 8 gigabytes, you still end up with a pretty big number. Okay, and putting all of those into one single folder still means it's kind of hard to find the DVD that you want, because you have a long list of DVD titles in one single folder. Now, if you have even smaller files like images, okay, who has a digital camera? Come on, the rest of you probably has one. You don't want to raise your hand, right? Okay. How big is an image file from a regular digital camera? Even with a 16 megapixel camera, if you save it as a JPEG, the JPEGs tend to be about 6-7 megabytes, right? So how many 6 or 7 megabyte files do you need to fill up 3 terabytes? Lots, right? Yeah. So imagine putting all those files into one single folder, and they're all called img right? And I want to find that picture with I want to find that picture that we took last Christmas.
That's what an alphanumeric filing system is for.
Well, that's what tagging is for.
I don't use that. I organize my stuff alphanumerically when I have a lot of files in one folder.
Okay, but sometimes sometimes you cannot index it with one single thing, because with photographs you can index by people, you can index by location, you can index by season or date, festival or whatever. You can also index by rating, like this is a high quality picture, this is not so good, motion blur and stuff like that. So there are multiple ways to index a picture. That's why tags are useful, because they're not exactly one single index. You're just looking for one specific thing. But getting back to the point here, that's basically things without top-down design. Okay, without hierarchy, it's one single flat thing, and it becomes pretty hard to manage everything. Another example that I usually use is Google Maps. Okay, so we'll just go to maps.google.com. And we can get rid of that. And then we can look at the entire United States here. It will show it in time. All right, there we go. Where's Sacramento? Well, you guys know, approximately where Sacramento is, but it doesn't show on the map, does it? Where's ARC? Where's this classroom? It doesn't show, right? But we know, ARC is somewhere in Sacramento, and Sacramento is somewhere in California, and California is on that map. So the question is, why is it not showing all the details down to this classroom?
If we were to show all the details and all the names, roads, and all that, it would be just a jumbled mess.
It'll be a jumbled mess. Well, yes, that's true. Okay, but some people will say, but we don't have enough resolution on this screen. This screen is only capable of 1024 by 768 or some resolution, right? So the text will require much finer resolution to do that. So let's just say that this screen is magical and it has infinite resolution. Okay. In other words, we can print it so small that we can use a magnifying glass or microscope to read it. So it can encode everything that we want on it. Would you still be able to find it? Probably not. Okay. And it's the same thing. It's the same thing here. We use top-down design. Okay. We look at the entire United States. If you know that Sacramento is in California, then we just go ahead and focus on California. But as you zoom in, you can start to see more things. And then you see Sacramento here. Good. Okay, we'll go in and zoom into Sacramento. And zoom in a little bit more. And you can start to see the smaller neighborhood, the names of the neighborhoods. And then we can go in a little bit more. Wait. Wait some more.
Is that a bottleneck?
No, I think it has to do with something is not working right. It's just being extremely slow for some reason.
What bandwidth do we have here?
The bandwidth is supposed to be pretty good.
Give you the United States of Gray. The United States of Gray.
Oh, it's gray. Okay, so now we can actually look into the neighborhood around here.
I can see my house from here.
It's one of those dots. Yes. Okay, but you guys get the point. Okay, so every time I zoom in, it displays more details. Every time I zoom in, it displays more details, and that has to do with how many things we can track at any particular time. How many people still remember those days? Some of you are too young to remember those days because those days were before your time. How many people still remember, your parents, would go to AAA, okay, CAAA, California Automotive Association of America, to get the free maps because, once you're a member, you can go get all the free maps. And, you open up a map and then you try to find a particular place, right? That's how we used to do things, okay? You give me an address, I have to find out where that place is in a physical map. Now, how do I do that? If I don't have any approximate idea of where that place is,
You have an index.
there's an index, very good. Okay, so you first use the alphabetical sorting to go to the index, find out which grid or which square that place belongs to. And sometimes it belongs to like multiple squares because it's a long street or something. Then you flip the map and then you go through those particular squares. But within a square, how do you find a particular court or a particular street, a particular circle? You scan for it, right? I mean, you have to basically scan, and see if you can find it. Okay, so those are the days when we have to do it, like that, and it's no fun. Okay, it's no fun because first of all you have to fold a map, and there's no table big enough to unfold the entire map. And then the index is always on the opposite page, not the page that you want to go to. Okay, so you have to flip the map, find the index, okay, it's K6, okay, go flip the map, go to K6, and then you have to find, within that little square, you have to find, the street name that you're looking for, and the print is so tiny that it is really hard to read. Okay, and the difficulty has to do with how much things we can track at any particular time. Okay, how many things can you track at any particular time? Short-term memory.
7 plus
7 plus or minus 2. That sounds about right. I mean, so 10 is really good. Someone who can track 10 things at a time is really good. But I don't think anyone can track like 50 things or 100 things at a time. There are games that you can play online, where they can show you numbers, like they just flash the numbers by, and then you have to retype the numbers, and they will do other things to distract you to try to figure out how many things you can track at any particular time. So that's a good test, to really show that our short-term memory and how many things we can track at the same time is kind of limited. Okay, that really goes all the way back to programming. Because when you are writing code, or when you're writing pseudocode in this class, or C code in the next class, or whatever code you want to write in, it's language independent, okay? You are in the same situation. If you are writing an algorithm that has 50 lines, okay, then in order to understand, track, debug, and trace the algorithm, your mind actually has to keep track of many, many things at the same time. Okay. Now, using the trace mechanism that we do in this class helps a little bit because the columns really help to show, okay, you're tracking the values of each variable with every single row. So that really helps. But at the same time, you still have to match the end of this while to the beginning of the while because you have to remember where to go back to. You have to track this particular if has an end if on this line, because if the condition is false and there's no else, you have to skip all the way to the end of that particular conditional statement. So there's still a lot of stuff that you have to track, even using the trace mechanism that we talked about today. So that's why, in designing an algorithm, you really have to limit the number of lines that you use in a particular program. So in this case, there's also one physical consideration. Okay, it doesn't have to do with how many things you can keep track of. It has to do with how big your screen is, okay, or how long is your paper. What happens when you have a single algorithm that has, let's say, 300 lines? Your screen can only display approximately 80 lines at a time, okay, and that's really stretching it, okay. So what is the problem here? The algorithm is this long, but you can only physically display this much at a time. How do you find the end of a while that begins here and it ends here? Huh? Well, it's difficult. It can be done, but it's definitely not easy. Okay?
Turn your screen sideways.
Then you get 160 lines. It still doesn't cover the entire thing. In the good old days, when we still had fan-folded paper, we just print it out. How many people know what is fan-folded paper? Wow, that's more people than I anticipated, because many of you, should have no contact with fan-folded paper whatsoever.
I've never seen it in person, but I've seen pictures of it.
Ah, okay. Yeah. Yep.
Print banner.
Yep. It's still useful for that purpose. Yes, you can still print banners. Okay, so fan-folded paper, as the name implies, looks like an accordion. So it's basically a long sheet of paper that is fan-folded, like this. Okay. The nice thing about it is, because it is physically attached, so it's perforated. You can tear it, easily apart into individual pages. But if you don't do that, it's one big long piece of paper. You don't have to staple or glue or tape or anything to make one big long listing. So what you do, or what people used to do, is they print out their algorithms, programs, code on these fan-folded paper, and they would lay it out on the floor. Okay, so they would actually put it all the way up here, and then they just spread it out like this, and then they would use a ruler to match the beginning of a construct to the end of the construct, and they draw a line, using a long ruler to say, okay, so from here to here is one loop. And that's how they keep track of nesting, when it comes to really insidious long algorithms. Okay? The fact that they have to do it like this means the program is not structured correctly. Okay? When in my previous job, I was a developer, and I had to deal with one single subroutine that had not 300, but 500 lines. Okay, so 500 lines, as one single algorithm. So that should be pretty bad already. But no, it's not. That's not the worst part of it. The worst part of it is, it has a lot of go-tos. Okay, now we haven't really talked about go-tos in this class because it's a taboo word in programming. Okay, so we just usually say the G word. Okay, you don't use go-tos to say, oh, that G word thing. Okay, because with a go-to, you can go from any place within an algorithm arbitrarily to any other place within the same code. Okay, so tracking a program like that is nearly impossible. And it was impossible in my case. I gave up after a few days, and I just rewrote the entire thing using my own code, break it up into 10 or 20 subroutines and stuff like that. My boss did not like that. All right, so getting back to this part here, is each algorithm should only fit in about 40 lines or so if you are an experienced programmer. What if you are not an experienced programmer? I would probably shrink it down to 20 lines or so, just so that it's easy to look, easy to read, and easy to figure out what is going on. All right, so are there any questions about the physical limitation of why we want to limit an algorithm to between 20 to 40 lines? No questions? Okay. If you want to read, some complex algorithm, you can always go to Wikipedia. So we go to Wikipedia and type in, some really kind of long-ish, complex, algorithm, like quicksort. Quicksort is relatively complex. I wouldn't say this is like insanely complex, but it's complex enough to make a point. So we just go to the algorithm itself. This is one part of it. And here's another part of it. So these two parts need to be together, okay? They work together. So it's not one single long piece, but this is considered one of the more complex algorithms. If you want something more complex, let me see if I can find something that's slightly more complex. Merge sort. We'll talk about these algorithms again later on in this class. So merge sort has two parts. This is one part, which is the merge sort algorithm itself, and it has merge as a separate part. I think this is fairly complex already. If you just look at this algorithm, it has a while on the outer side. Okay, deselect. This while ends with this end while. This if is the entire thing inside the while, and then within that if we have another if then. Okay, they don't have end if here. I think they're just using a different pseudocode here. So these are fairly complex algorithms to begin with, but even these we separated because you can see that merge is a component of merge sort. In other words, if you are to merge these two into one, you will have to combine this code into this part of the original program. Yep.
You say like 20 to 40 lines of code. Do you mean just actual code that you can use on a computer, not the notes like you have there?
I guess to a certain point it depends on the density of your code. So if you have a lot of single line open curly brace and single line close curly brace, you can probably make it like instead of 40 lines, you can extend it out to maybe 50 lines or so, depending on the density of the code. But the whole point is you can only track so many things at the same time. So open curly brace and closed curly brace obviously are not really things that you need to keep track of, so it doesn't really count. So it has to do with how many constructs you have on the screen at any particular time. How many loops, conditional statements, assignment statements, and so on are being displayed at the same time. I guess that would be a good measurement of the complexity of the algorithm. Question? Okay. So getting back to our notes here. Well, the big problem now is if I want to put everything into 20 to 40 lines, doesn't that kind of limit the kind of algorithm that I can specify or that I can describe? Because some algorithms inherently require more than 20 lines to describe. So if the limitation is 20 lines per algorithm, doesn't that put a big limitation of the complexity of the algorithms that we can describe? Well, the answer is no, not really. Okay, because it goes back to the map concept. Okay, if you look at the map, so right here, I'm kind of guesstimating here. There are maybe about 50 to 70 names on the map right now. Okay, it's just a guesstimate. Please do not actually count it. Okay, that's not the point. Okay, the point is there are maybe about 50 to 70 names on the map at this point. But when you need to, we can zoom in and see more names. Okay, so that's the whole point. We want the algorithms to be about the same thing, where if you look at an algorithm at a particular zoom level, you only have about 20 things to worry about. But if you want to look into something, it will display more details. Okay, for instance, this is ARC. I can see ARC here. So if I want to move to a neighborhood that is closer to ARC, then I can actually center this and then zoom in a little bit more, and then I can see the names of the streets that are in the neighborhood of ARC. So I want to do something like that when I have to write my algorithm. In other words, my algorithm may be very complex, okay? Maybe it is the complexity of the entire Sacramento, which has a lot of streets, a lot of names, a lot of places, and so on and so forth. But I don't want to have to deal with all of those details all at once. I only want to deal with about 20 things at the same time. Is that making any sense? Kind of? So just imagine that you want to be able to zoom into the algorithm, one level at a time, and each level only has a complexity of about 20 to 40 lines. Are we still doing okay so far in terms of the rationale of top-down design? How many people have taken or is currently are taking an English writing class? Okay. What do you use? When you're asked to write a, let's say, 5-page essay, okay? Do you just sit down and go, okay, I'm just going to type like that? No. Sometimes.
But sometimes I have to. Sometimes
Okay.
it's 2 or 3 hours when it's good.
Okay. Well, even if it's due in 3 hours, you can still use the structure approach. But how do you do it? Yep.
The structure to it that has an introduction, sort of the body or beat of the paragraph, and then the final conclusion. So it has bullet points within each
Right.
paragraph that's very ordered, and you have to stay within those confines.
And even within the paragraph, you still have a microstructure because each paragraph starts with a sentence that connects either to a previous paragraph or is an introduction and say, okay, let's now talk about this. And it also has its own summary or a lead into the next paragraph, and then you have the stuff that is in between. So that means when you're writing in an English class, you're also using top-down design. Okay? Because what happens when you do not use the top-down design, and let's just say that you are already familiar with the subject matter that you're writing about, you already know all the details that you want to write about, but instead of using the top-down design where you just outline the entire thing and say, okay, I need to mention this, 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 and this in this particular order, but when I talk about this, I also have to separate it into these subtopics and then subtopics into paragraphs and so on. So instead of using a structured approach, you just decided, well, since I know this subject matter so well, I'm going to write my 5-page English paper from start to finish in one single stroke. What happens when you try to do something like that?
It's fractured.
It's fractured. You get lost, right? Yeah, 1 page and a half, into the writing, you go like, where am I? Why am I writing this? How does this relate to the whole paper, right? But I personally have those experiences. Okay, if I do not structure my articles, I would go right into, I would start writing. It's easy because I know the subject matter already. But halfway through, I'll go like, where am I? What do I do next?
Or you'll start digressing.
Or I'll start digressing. Yes, that happens too. But that usually only happens when I'm in a class where it's interactive. When I'm writing and it's not interactive, it's harder to get digressed. Yeah. Not putting the blame on you guys, but just saying.
Just find out the time. I admit full responsibility for getting us into a digression about the terminal velocity of raindrops.
That was a good discussion. So anyway, I just want you guys to understand the rationale of top-down design, and then the later part of this particular module has an example of top-down design using factoring. Okay, so if you're forgetting about factoring, from elementary school, you might want to just kind of brush up a little bit on factoring, and then we'll talk about it on next Tuesday. If you have any questions related to exam 1, you want to bring those questions to me on Tuesday too, because that's the last chance to talk about it. All right. And does anyone have my row sheet?
I do.
Oh, okay. Thank you.
I need to ask the same.
Yep, here you go. You're not back on the list yet?
Since you took me off.
Okay.
Because I noticed you got a new list.
Yes.
And I'm not able to do it.
Okay, so that means you need to.
$1.25.
Did you go through the petition form or?
No, we went to I went with you to the office, and all she said you had to do is fill out that one form because you want to drop me in.
And I
So,
did.
Yeah, we filled it out and you sent it in, but I guess they ain't got it done at the admin office.
I did that already.
Yeah, 'cause we
I'll
did that
double
together.
check.
Yeah, we did that together.
Yeah. Okay, so your name is.
LaForce. James. student number is. One's.
Oh, that's okay. Yeah, that's okay.
And J.
Okay, so I need to double check and make sure that.
Okay.
Check.
And then, in fact, if they don't have it done by Friday, then I'll check with them Monday morning. Before I come to class, I'll walk in the admin office and ask them, make sure they got it.
Now, do you remember whether I did a?
Yeah, you did. She gave you a little small form. You had to fill out all at once. It's a small one.
Right.
Sucker wasn't about that small.
Right.
You filled it, and I signed it with you. So I remember you put it in a Holy Joe, and then we stuck it in.
Yeah.
A whole lot. 'Cause I
Okay, so that means that it has been filed. It's just not processed over there.
Right.
Okay, that's good.
I'll just check with them on Monday, make sure they got it.
Yeah, that's kind of important. So,
Okay.
Yep.
Okay.
All right.
Yeah, I'm just having trouble understanding. That's why I asked if you do the first, because I'm having trouble understanding some of the concepts you're doing. I'm just trying to catch on what's what, and that's what I was asking you to do. That's why I asked you a while ago about to do number 2 again, to
Mhm.
record it, because I'm gonna have to watch those so I can catch what's what. So I understand. That's why I was asking.
So number 2, you want to redo and do a recording.
Yeah, that's the only reason why I ask.
Okay.
Because what I'm gonna spend all Sunday doing is watching and trying to catch the. Because that way, once I know what goes with what, like when you say pre, okay, I'm like, okay, where does it come from? Where you? So I got to figure out what. And once I catch that concept, then I'll be able to catch up with what's going on.
Okay.
So I just got to catch that.
All right.
Cool.
Mhm.
So I fixed the issue.
Oh, what was it?
When the NVIDIA or not NVIDIA, the ATI drivers, proprietary drivers were installed, it was pointing to a false halt signal.
It was pointing to a what?
A